All right, so first I wanted to go through what this data would look like if we had a larger sample size on that screen that showed our sample where we think we did an N of 10 and then an N of 40. So you can see here on this screen, if we were in the situation where we did an N of 10, only 10 clicks, we had students getting between 40 and 90% of their clicks being water, between 4 and 9. When we increase that to 40 clicks, now we're down to a point, like, what is that, 50% to 85%? So we've really brought down that spread quite a bit. Both of these distributions seem to be centered around 0.7-ish, around 70%. So this is sort of the trend that we expect to see in these situations. We expect our mean to stay the same because it's going to be close to the real proportion of Earth covered in water, but that we see a spread decrease because the more information we have, the closer we should get to the real value. So let's go ahead and demonstrate this in StatCrunch. So I'm going to open up StatCrunch, and I'm going to go ahead and dump into an applet. So let's simulate some, sure, coin flipping will work. Seems like we're flipping a coin whether we hit water or not. Let's just say I think they eventually tell us the proportion of the Earth covered in water is 71%. I could be misremembering that. And let's go ahead and first we're going to do the 10 clicks, 10 coins. So compute. If we do this once, it does the same painful thing we did. And then it's going to pop down one observation. If we do this 1,000 times, it's going to do that 1,000 times for us. This is way more efficient than us clicking around on a map is to just have something do it for us. So here we can see we end up with our mean right around, like the tallest bar right around 0.7, but we have variations. Ooh, I want this to be in proportion land. Ooh, edit, proportion. Whew, there we go. I was like, something is off. There we go. 0.7. All right, so we're still centered around 0.7. We can see that's about the tallest bar is at 70%. We don't have quite the unimodal symmetric distribution we might expect, but if we think about that rule of thumb for our binomial to be approximately normal, NP and NQ, we're not quite there yet. Let's go ahead and change this once more. Let's look at what happens when we do 40. If we think now about that rule of thumb, we're getting a little closer. 40 times 70%, that's about 28. That leaves me 12. Yeah, so I would actually have my rule of thumb. So let's look. Okay, she's looking a little funky. That's what happens with randomness. If I take this more and more and more, I'm going to start seeing that normal distribution centered right around my 0.7. But if we looked at the actual values this is taking, now we're going from about 0.45 to 0.9 something, right? And the majority are between the 0.6 and 0.8. This is not what we saw when we did this for 10. I wish I could keep both of these up. I don't know if I can. When we did this for 10, look at the numbers here. We're going all the way from 0.2 to 1. So a lot more spread. So you can play around with this. Again, the applet I used, I went in here and said, let's just do some simulations. Seems to me if we're talking about proportions and something that's yes, no, it's pretty much related to coin flipping. And then I forgot to originally flip that, change that to proportions. And then we can see those bars, each value in those bars, each one of those 1,000 things represents a sample of whatever size I choose. So that's that really important idea of if I wanted to describe one sample, I would use a bar chart because technically my variable that's underneath all of this is categorical. But if I want to talk about all of the possible samples that I could take, now I'm looking at something numeric and I'm going to describe that or use a histogram to talk about it. So hopefully that helps a little bit. So let's see if you if you remember what I just said about what happens as our sample size increases.